Hello dear students, in this class I am going to discuss about the variation of magnetic field due to its distance. In the previous class already I had discussed about the magnetic field due to the circular coil for one turn and for n turns. In previous video already I discussed about that concept, that is B is equal to mu naught divided by 4 pi 2 pi I into r square divided by x square plus r square whole to the power of 3 by 2, which is the expression for magnetic field due to the circular coil or magnetic field due to the current carrying circular loop. It is called expression for the magnetic field due to the circular coil or magnetic field due to the current carrying circular loop. B is equal to mu naught divided by 4 pi 2 pi into I into r square divided by x square plus r square whole to the power of 3 by 2. Or in vector form we can write this equation. In vector form we can write this equation, that is vector B, magnetic field. It is a vector quantity. The SI unit of magnetic field is Tesla and the CCS unit of magnetic field is Gauss. Here the magnetic field vector B is equal to mu naught divided by 4 pi into 2 pi I r square divided by x square plus r square whole to the power of 3 by 2 into unit vector I. Unit vector I. This is the vector form of the magnetic field due to the circular coil on the axis of the axial line or from the center of the coil, and it is also called expression for the magnetic field due to the current carrying circular loop. It is only for one turns. Suppose it consists of n number of turns. For n turns we can write this equation. For n turns we can write this equation. B is equal to mu naught divided by 4 pi 2 pi into n into I r square divided by x square plus r square whole to the power of 3 by 2. This is for n number of turns. This is only for one turn. This is only for one turn and this is for n turn. Suppose now I consider this is a circular coil. This is a circular coil. Here this circular coil consists of only one turn wire. Due to this one turn wire, when the current is flowing in this circular coil, the magnetic field is produced around this circular coil. Magnetic field is produced around this circular coil. Now I consider that circular coil is here. This is the circular coil and R is the radius of the circular coil. When the current is flowing in this circular coil, the magnetic field is produced. Now I have to find the magnetic field at this point P from the center of the circular coil with the distance x. With the distance x. This is the circular coil. From this center of the circular coil, the magnetic field at this point P. If the distance is increases, the magnetic field is decreases. If the distance is decreases, the magnetic field is increases. It is a very simple concept. ಇಲ್ಲಿ ಒಂದು ಸರ್ಕ್ಯುಲರ್ ಕಾಯಿಲ್ ಇದೆ ನಮ್ಮ ಹತ್ರ. ಸರ್ಕ್ಯುಲರ್ ಕಾಯಿಲ್ ಅಲ್ಲಿ ಕರೆಂಟ್ ಅನ್ನು ಪಾಸ್ ಮಾಡಿದಾಗ ಏನು ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತೆ ನಮಗೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತೆ. ಈ ಸರ್ಕ್ಯುಲರ್ ಕಾಯಿಲ್ ಇಂದ ನಾವು ದೂರ ಹೋದಂತೆ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಏನಾಗುತ್ತೆ, ಕಡಿಮೆ ಆಗುತ್ತೆ. ಸರ್ಕ್ಯುಲರ್ ಕಾಯಿಲ್ ಇಂದ ನಿಯರ್ ಕಡೆ ಬಂದಾಗ ಏನಾಗುತ್ತೆ, ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಜಾಸ್ತಿ ಆಗುತ್ತೆ. It is a very simple concept and it is an imaginary concept. If the distance is increases from the center of the coil, the magnetic field is decreases. If the distance is decreases towards the center of the coil, the magnetic field is increases. Here, this is the circular coil. The center of the circular coil, the magnetic field is uniform, and the near end of the circular coil, the magnetic field is non-uniform. Now I draw the variation of magnetic field due to the circular coil graph. Now I consider this is the center of the coil. Here O is the center of the coil and the B is the magnetic field. And in this graph, this diagram shows or this graph shows the variation of magnetic field due to the circular coil. The variation of magnetic field due to the circular coil. This is along the positive x direction and this is along the negative x direction. The magnetic field is decreases on both the axes. If the distance is increases, the magnetic field is decreases. If the distance is decreases, the magnetic field is increases. Then the center of the coil, here at this point the magnetic field is maximum. If the distance is increases, the magnetic field is minimum. And this graph shows the variation of magnetic field due to the current carrying circular coil or the variation of magnetic field due to the current carrying circular loop. If the distance is 0 or it is at the center of the coil, the magnetic field is maximum. If the distance is increases on its either side, the magnetic field is decreases. This graph shows the variation of magnetic field due to the current carrying circular coil. Suppose here this point P is the point at which the magnetic field is to be calculated. Suppose now I consider here this distance in this equation. Suppose the point is located at the center of the coil. Then x equal to 0. If the point is lies on the or located at the center of the circular coil, x equal to 0. When x equal to 0, then the magnetic field equation here, this equation becomes B is equal to mu naught divided by 4 phi. When x equal to 0, then you write this equation as 2 phi n into I divided by 2 phi n into I divided by R. 2 phi n into I divided by R. Put x equal to 0 in this equation. When x equal to 0, this value becomes B is equal to mu naught divided by 4 phi 2 phi n I divided by R. For only one term, you write this equation B is equal to mu naught divided by 4 phi 2 phi I divided by R. For n terms, 2 phi n into I divided by R. Or also you can write this equation. This is 2 1s are 2 2s are here 5 get cancelled. We get B is equal to mu naught divided by here mu naught into Ni. B is equal to mu naught into Ni divided by 2R. Which is the expression for magnetic field at the center of the circular coil. Here P is the point at which the magnetic field is to be calculated. But this point lies at the center of the coil. Then you get this equation B is equal to mu naught n into I divided by 2R for n number of turns. For only one turns n equal to 1, then you get this equation mu naught into I divided by 2R. At this point, the magnetic field is maximum. This is about Biot-Savart's law, and using the Biot-Savart's law, we find the magnetic field due to the circular coil at the center and far away from the circular coil. From using this concept, now I imagine this is the straight current carrying wire. Here, in this straight current carrying wire, when the current is flowing in this direction, the magnetic field is produced around this wire.
Now, I state the right hand rule or right hand thumb rule. In previous classes, already I had discussed about the left hand rule or left hand thumb rule. The first three fingers of our left hands are stretched mutually perpendicular to each other. Thumb, here forefinger indicates the direction of the magnetic field. Middle finger indicates the velocity of the charged particle, and thumb indicates the force acting on the charged particle. In this class, now I discuss about the right hand thumb rule. When the current is flowing in this wire, the magnetic field is produced around this wire. The magnetic field is produced around this wire. Now, the right hand thumb rule, it states that the current carrying wire, this is the current carrying wire. Right hand rule or right hand thumb rule, it states that the current carrying wire or the current carrying conductor is enclosed by the right hand or enclosed by the palm of the right hand. Enclosed by the palm of the right hand. Thumb indicates the or thumb pointing the direction of the current. Here thumb pointing the direction of the current, and rest of the fingers indicates the direction of the magnetic field. Rest of the fingers indicates the direction of the magnetic field. It is a very simple statement. The right hand rule or right hand thumb rule, it states that the current carrying wire or the current carrying conductor enclosed by the right palm, thumb indicates or thumb pointing the direction of the current, and curled finger indicates. The curled finger means it is in the form of circular ring. Here the curled finger indicates the direction of the magnetic field. It is a one statement. This is for straight wire. Now I state another statement. Now I discuss another statement. This is the circular coil. When the current is flowing in the circular coil, the magnetic field is produced. When the current is flowing in the circular coil, the magnetic field is produced. For this circular coil, the right hand thumb rule or the right hand rule states that here, if I enclose the right form in this circular coil, this is the circular coil, right form in this circular coil. Here thumb indicates the direction of the current. Again, thumb indicates the direction of the current in this circular coil, and other finger indicates the direction of the magnetic field. Other finger indicates the direction of the magnetic field. This is for circular coil. Here right hand thumb rule. The right hand thumb rule or right hand rule states that any conductor or any circular wire, a straight wire enclosed by the right palm, thumb indicates the direction of the current and other finger indicates the direction of the magnetic field. This is the right hand thumb rule. From using this right hand thumb rule, now I discuss about another concept, Ampere circuital law and its application. Up to here I discuss about Biot-Savart's law, and using that Biot-Savart's law, magnetic field due to the current carrying circular loop or magnetic field due to the circular coil. This is the expression for magnetic field due to the circular coil or magnetic field due to the current circular loop. This is for one turns and this is for n turns, and it is the vector form, and this is the expression for magnetic field at the center of the coil. The point P is located at the center of the coil, then x equal to 0. When x equal to 0, then you get this equation, B is equal to mu naught n into I divided by 2R. Okay dear students, the next concept of your topic is Ampere's circuital law. Have you heard the name Ampere? Ampere is the SI unit of current. The current means the rate of flow of charge is called current, and current it is mathematically denoted by the symbol I. I is equal to Q divided by T. I is equal to Q divided by T. Coulomb per second or ampere is the SI unit of current. Now I am going to discuss about Ampere's circuital law.
Ampere's circuital law.
Ampere circuital law, it states that
the magnetic field around any closed path in vacuum or air is equal to mu naught times of total current enclosed by that path.
this is the statement of Ampere's circuital law. Ampere is a scientist. The SI unit of current is ampere. Now I discuss about the concept of Ampere's circuital law. Ampere's circuital law. Suppose if you are consider
one surface, this is the closed surface. This is a closed surface. And the current is flowing in this coil or in this surface. Here. This is the direction of current flowing in this surface.
When the current is flowing in the surface, the magnetic field is produced. The magnetic field means the region around the current carrying wire is called magnetic field. What is the source of magnetic field? Moving charge particles. Moving charge particles are the source of magnetic field. Or in other words, the region around the magnet is called magnetic field. In this law, it states that the magnetic field around any closed path. This is the closed path. The magnetic field around any closed path in vacuum or air is equal to mu naught times of current enclosed by that path. Mu naught times. Here mu naught means this is the permeability of free space. Permeability of free space. The statement, it states that the magnetic field around the any closed path. This is the closed path. The magnetic field around the any closed path in vacuum or air is equal to mu naught times of. Mu naught means it is the permittivity of the free space. The mu naught times of total current enclosed by that path. It is mathematically denoted by the line integral of. It states that the line integral of. Here put another word. It states that the line integral of. The statement of this Ampere circuital law is, it states that the line integral of magnetic field around the any closed path in vacuum or air is equal to mu naught times of total current enclosed by that path. Here this symbol, this is the integration symbol. Here this is the circle. This is read as the line integral of magnetic field. Magnetic field, it is mathematically denoted by the symbol V. It is a vector quantity. The line integral of the magnetic field. Now I consider the small current element on this closed loop, that is dl. B is the magnetic field of this closed path, and D is the, or dl, this is the current element of this closed path.
current element of this closed path B into the current element of this closed path is equal to mu naught times of the total current. Mu naught times, mu naught means it is the permeability of the free space. Mu naught times of the total current enclosed by that path. Mu naught into I. This is the mathematical form of the Ampere circuital law. Mathematical form of the Ampere circuital law. Here B is the magnetic field around the closed path. dl is the current element or the small current element on the closed path, and mu naught is the permeability of the free space. I is the current in the closed path. This is the mathematical form of the Ampere circuital law. It states that the line integral of the magnetic field around any closed path. This is the one closed path. Now you consider the one path. This is the closed path. This is also called Amperian loop. It is called Amperian loop. It states that the line integral of the magnetic field around any closed path in a vacuum or in an air is equal to mu naught times of the total current enclosed by this path. Here this is the closed path. In this closed path, now I consider one small current element. This is the dl, and the line integral of magnetic field due to this current element is equal to mu naught times of net current enclosed by that path. This is the very simple statement. What is the use of this what is the use of this Ampere circuital law? Now yaake kalibekiದ್ರೆ Ampere circuital law idra use ಏನೈತೆ ನಮಗೆ? The statement of this Ampere circuital law is, it states that the line integral of the magnetic field around any closed path in a vacuum or air is equal to mu naught times of net current enclosed by that path. This is the mathematical form of the Ampere circuital law. Here B is the magnetic field around the closed path, dl is the current element around the closed path, and I is the current in a closed path. Mu naught is the permeability of the free space. What is the use of this circuit? Ampere circuital law. From using this Ampere circuital law or Ampere circuital law gives the relation between current in the wire and magnetic field produced around it. Now you have consider any straight wire. This is the straight current carrying wire. Ampere circuital law gives the relation between current in this wire and the magnetic field produced around this wire. This is the use of Ampere circuital law. ಒಂದು ವೈರ್ ಅಲ್ಲಿ ಎಷ್ಟು ಕರೆಂಟ್ ಫ್ಲೋ ಆಗುತ್ತೆ, ಆ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗೋದ್ರಿಂದ ಎಷ್ಟು ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ ಪ್ರೊಡ್ಯೂಸ್ ಆಗುತ್ತೆ, ವಾಟ್ ಈಸ್ ದ ರಿಲೇಷನ್ ಬಿಟ್ವೀನ್ ದ ಕರೆಂಟ್ ಅಂಡ್ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್, ಅದ್ರ ಬಗ್ಗೆ ನಾವು ಸ್ಟಡಿ ಮಾಡಬೇಕಾಗಿತ್ತು ಅಂದ್ರೆ ಯಾವ ಈಕ್ವೇಷನ್ ಯೂಸ್ ಮಾಡ್ತೀವಿ? ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟಲ್. ಇಟ್ ಗಿವ್ಸ್ ದ ರಿಲೇಷನ್ ಬಿಟ್ವೀನ್ ದ ಕರೆಂಟ್ ಇನ್ ದ ವೈರ್ ಅಂಡ್ ದ ಮ್ಯಾಗ್ನೆಟಿಕ್ ಫೀಲ್ಡ್ produced around it. And the second point, ಮತ್ತೆ ಏನಿದೆ ಇದರ ಯೂಸ್? Here the closed path around the current carrying wire, is called Amperian loop. This is called Amperian loop. Amperian loop ಅಂತಂದ್ರೇನಿ? The closed path around the wire. The closed path around the wire is called Amperian loop. And the third point, it is applicable only for a steady current. Ampere circuital law, it is applicable only for circular current with respect to time. Suppose the current is fluctuate with respect to time, it cannot be applicable. It is applicable only for a steady current. ಹೌದಾ? ಈಗ 1 ಆಂಪಿಯರ್ ಕರೆಂಟ್ ಫ್ಲೋ ಆಗ್ತಿತ್ತು ಅಂತಂದ್ರೆ ಕಂಟಿನ್ಯೂಸ್ ಆಗಿ 1 ಆಂಪಿಯರ್ ಕರೆಂಟೇ ಫ್ಲೋ ಆಗಬೇಕು. ಸಪೋಸ್ ಒಂದು ಮೊದಲನೇ ಸೆಕೆಂಡಿಗೆ 1 ಆಂಪಿಯರ್ ಆಗಿ, ನೆಕ್ಸ್ಟ್ ಸೆಕೆಂಡಿಗೆ 0.8 ಆಗಿ, ನೆಕ್ಸ್ಟ್ 0.7 ಆಗಿ, ಆಮೇಲೆ 1.5 ಆಯಿತು ಅಂದ್ರೆ ಆ ರೀತಿ ಇರ್ತಕ್ಕಂಥ ಸಂದರ್ಭದಲ್ಲಿ ನಾವು ಆಂಪಿಯರ್ ಸರ್ಕ್ಯೂಟಲ್ ಲಾನ ಅಪ್ಲೈ ಮಾಡೋಕ್ಕೆ ಪಾಸಿಬಿಲಿಟಿ ಇಲ್ಲ. ಇಟ್ ಈಸ್ ಅಪ್ಲಿಕೇಬಲ್ ಓನ್ಲಿ ಫಾರ್ ಎ ಸ್ಟಡಿ ಕರೆಂಟ್. Suppose the current is fluctuate with respect to time, the Ampere circuital law is cannot applicable for that type of condition. And
Here, it is applicable for closed path. It is applicable for closed path. The current is moving, or the magnetic field is produced around the closed path. The magnetic field is produced around the closed path. Then it is called Amperian surface, Amperian loop or Amperian surface. It is used in magnetism. It is used in magnetism. Suppose it is called a surface. Now in this condition, I consider this is as a loop or closed path. This is called Amperian loop, and this Amperian loop is help us to study the magnetism in case of Ampere's law or Amperian loop. But instead of this loop and this path, I use the word the surface of this loop. It is for Gaussian surface. It is for Gaussian surface. This is the relation between electrostatic and magnetism, and it is the use of Ampere's circuital law. Ampere's circuital law, it states that the line integral of magnetic field. ಇಲ್ಲಿ ಇರತಕ್ಕಂತ ಸಿಂಬಲ್ ಅನ್ನು ಯಾವ ರೀತಿ ರೀಡ್ ಮಾಡ್ತೀವಿ ನಾವು? The line integral of magnetic field around any closed path in vacuum or air is equal to mu naught times of total current enclosed by the path. ಇಲ್ಲಿ ಒಂದು closed path ಇದೆ. Here this is the current carrying circular wire. ಒಂದು circular wire ಇದೆ. It consists of one term or n number of terms. dl is the current element. Current element means it is the smallest portion of the wire. The smallest portion of the current carrying wire. And Amperian loop means it is the closed path around the wire or around that circular wire. And mathematically it is denoted by the symbol the line integral. It states that the line integral of the magnetic field around any closed path in vacuum or air is equal to mu naught times of net current enclosed by that path. This is the mathematical form of the Ampere circuital law. From using this Ampere circuital law, we find the relation between current in the wire and the magnetic field produced around it. There are three applications in your syllabus. The first one is magnetic field due to the long straight wire, and magnetic field due to the solenoid, and magnetic field due to the toroid. Now I will discuss about the applications of Ampere's circuital law. The first application is the expression for the magnetic field due to the long straight current carrying wire. In case of electrostatics, already we will discuss about the electric field due to the long straight current carrying wire. In this topic, we will study about the magnetic field. In the unit 1, we study the electric field due to the long straight current carrying wire. In this unit 4, we will study about the magnetic field due to the long straight current carrying wire. That is the first applications of Ampere circuital law. Now, I am going to discuss about the first application of this Ampere circuital law. Okay, dear students, now I discuss about the applications of Ampere circuital law. Applications of Ampere's circuital law. The first application is magnetic field due to a straight current carrying conductor. Magnetic field due to a straight current carrying conductor. This is the first application of Ampere circuital law. Now I consider a straight current carrying wire. This is the straight current carrying wire. Here I is the current in the wire. When the current is flow in this wire, the magnetic field is produced around this wire. This is the familiar concept and very simple concept. When the current is flowing in the wire, the magnetic field is produced around this. And
I is the current in this wire. When the current is flow in this wire, the magnetic field is produced around this wire, and magnetic field due to straight current carrying conductor. Due to this current carrying conductor, the what amount of magnetic field or how much amount of magnetic field is produced around this wire. Now I am going to calculate that part. Here, P is the point at which the magnetic field is to be calculated from this wire with the perpendicular distance at a r. With the perpendicular distance at a r. P is the point at which the magnetic field is to be calculated at a distance r or perpendicular distance r from this current carrying wire. The current is flowing in this direction. The magnetic field is produced around this wire. The magnetic field is produced around this wire. The P is the point at which the magnetic field is to be calculated. Magnetic field is to be calculated, and here the R is the radius of this closed path. Now I consider R is the radius of this closed path because it is the application of Ampere's circuital law. R is the radius of this closed path. This is called Amperian loop. This is called Amperian loop. Amperian loop means it is the closed path of around the current carrying wire. The closed path around the current carrying wire is called Amperian loop. The closed path around the current carrying wire is called Amperian loop. When the current is flowing in this direction or the current is flowing in this conductor, the magnetic field is produced. The P is the point at which the magnetic field is to be calculated at a perpendicular distance r from this conductor. Here, to find the magnetic field at a point P, the Amperian loop is considered as a sum of the n number of current elements along this Amperian loop. This is the Amperian loop. This Amperian loop is considered as a current element. It is this Amperian loop is made up of the n number of current elements. In that n number of current elements, now I consider one current element. This is the small current element. dl is the current element and B is the magnetic field. It is a vector quantity. Here the current element, the direction of the current element and magnetic field moving in the same direction. Suppose if you consider the current element in this direction, the magnetic field is moving in this direction. You consider the current element here, the magnetic field is moving in this direction. The current element is here, the magnetic field is moving in this direction. This is an imaginary part. Amperian loop means it is the closed path around the current carrying wire. The closed path around the current carrying wire is called Amperian loop. This Amperian loop is used to find the magnetic field due to this conductor. From using this Amperian loop, now we have to find the magnetic field due to this conductor. Magnetic field due to this conductor. From using the statement of Ampere's circuital law, from Ampere's law, we know that the statement, the line integral of the magnetic field due to the current element is equal to mu naught times of the total current enclosed by that path. This is the statement of Ampere's circuital law. From this Ampere's circuital law, from using this Ampere's circuital law, here, when the current is flowing in this conductor, certain magnetic field is produced. Certain magnetic field is produced. To find this magnetic field, we use this Amperian loop. From using this Amperian loop, we have to find the magnetic field at this point. The line integral of B dot dl is equal to mu naught into I. This is the statement of Ampere's circuital law. We know the formula. Vector A dot B is equal to AB cos theta. A dot B is equal to AB cos theta. Then I write this equation. The line integral of B dl, vector B dot vector dl is B dl into cos theta is equal to mu naught into I. This is equation number 1.
Equation number 1. In this equation number 1, here B is the magnetic field, D is the current element, but to find the magnetic field due to this total Amperian loop, then you sum this value. Take the magnetic field value outside. The line integral of the dl into cos theta is equal to mu naught into I. Here, the line integral of the dl is equal to, dl is the current element and this Amperian loop consists of n number of current elements. The sum of all these current elements is, that is the line integral of dl. How to calculate this value? From using this integration symbol. This is the circumference of the circle, or the circumference of the Amperian loop. Circumference of the Amperian loop, that is equal to 2 pi r. The circumference of the Amperian loop is 2 pi r, and the cos theta, the angle between B and dl. Here, the angle between B and dl is the angle between B and dl. The angle between B and dl, theta is equal to 0 degree, because both are moving in the same direction everywhere on this Amperian loop. The angle between B and dl, theta equal to 0 degree. There is no angle between the B and dl everywhere on this Amperian loop. Then theta equal to 0 degree. Cos 0 degree value is 1. Cos 0 degree value is 1. Then you write this equation as B. Here, the magnetic field B into the line integral of dl, that is circumference of the circle, 2 pi r into cos theta. Cos 0 degree value is 1. Then B into 2 pi r is equal to mu naught into I. Then magnetic field B is equal to mu naught into I divided by 2 pi r. B is equal to mu naught into I divided by 2 pi r, which is the expression for magnetic field due to the long straight current carrying wire, or long straight current carrying conductor. B is equal to mu naught into I divided by 2 pi r. This is the first application of Ampere's circuital law. It is the very simple. Thank you. In the next class, I will discuss about magnetic field due to the solenoid and magnetic field due to the toroid. Thank you.